So welcome everyone to the 2011 Western Region Annual Post Doc and New Scientist Colloquium. We've got a lot of activities planned for the afternoon, so let's not spend too much time talking about that. As soon as I'm done with this little overview, we're going to hear from Rama. He's going to talk a bit about the Mendenhall program and its health, as well as the Office of Science Quality and Integrity. Then we're going to have a panel discussion with postdocs, new scientists, and research advisors and mentors. So it will be an interactive session. We'll have a really, really rousing discussion. It really was something that I found as a high peak from last year's colloquium myself, anyway. Then we're going to have brief presentations by 14 new USGS scientists. We're going to hear talks about soil carbon cycling and terrestrial land cover change, toxic metal geochemistry, sediment transport, groundwater flow modeling, seismic and paleoseismic studies, as well as a bit about some paleoclimatology. And then we'll follow those brief presentations with a poster session with refreshments. So that's all I wanted to say at the very beginning, and with that I'm going to go ahead and cue up Rama. All right, there you go.
Thank you, Jason. I think I got this mic thing you worked out, and let me know, Mike, in the back if I don't. So thank you for coming to the 2011 edition of the Western Region. I guess I'm calling it just Western. I dropped the region, but Western Post Doc New Scientist Colloquium. And I want to start off with an acknowledgement on behalf of everybody here for all the hard work that's done by a number of people that are here in Menlo Park. I've just been somebody who's been cheering this on from a distance in Virginia. So let's acknowledge Jason Addison, the gentleman with the tie here, who's been putting an enormous amount of energy into organizing it this year. And then let's not forget the gentleman with the hat in the back room there. That's Michael Moore, who is helping us to stream this as well as archive it, and so future generations can see this great show that's going to be happening today. And then we can acknowledge the panel when they come up here and do their thing a little later on. Let's not forget Darcy McPhee back there, who, among other things, is also, I think, coordinating snacks, a very important part of the activity. Steve Ingebrigtsen is not here. I think he's in the Sierra somewhere enjoying himself, is what I understand. And then Kristen Bird, who is also not here, was another member of the informal organizing committee. So thanks to everybody for making this possible. I'm just going to run through a few slides here, give you a very quick update on the Mendenhall program. And I want to say first off that not everybody who's in this are necessarily, came to the USGS through the Mendenhall, so by no means is Mendenhall the only way that one can start to do post-PhD work at the USGS. But because there's a significant amount of interest in that program on this campus, I thought I'd give you a quick update on it. And then also a little bit about the Office of Science Quality and Integrity. This is a new office that's been created at the USGS back in October as a part of the realignment of the USGS. The Mendenhall program now resides in the Office of Science Quality and Integrity, and so I'll give you a little more information on the mission of the office and how the Mendenhall fits into the overall mission of the Office of Science Quality and Integrity. Okay, well, just jump right into what is OSCE. Basically, this is an entity that has been something that has been discussed and talked about for any number of years, at least in Reston, that at the Office of the Director level, that there is a need for a group of some size to basically worry about, bottom line, the health of science at the USGS. Not to say that program coordinators or center directors, former team chiefs and others don't already do this in spades, but to look at it at an integrated way all across the USGS, to look at some broad issues that influence and impact the way we do our science, the way we communicate it, and therefore the health of USGS science. So partly to develop some strong practices, common shared practices, hopefully, and also to help develop policy and to support the programs, the science programs. A certain amount of the focus initially is going into standardizing policy across the Bureau to help increase efficiency. And an example of that is the RGEG process that some of you may have already experienced. It is with the Office of the Director. We're directly under Suzette Kimball, who's the Deputy Director, and we work closely with virtually all parts of the organization. So all of this, what OSCE does and what many of us do, are tied to the science strategy of the USGS, or the strategic directions as articulated in a science strategy document that was published a couple of years ago. Some of you, many of you may be aware of, or you've been involved in the science strategy teams associated with the mission areas, where they're looking at the next 5 years and beyond in terms of the kind of focus that the science USGS does and how that is going to serve the major goals identified in the science strategy. And so the same thing for us in the Office of Science Quality and Integrity. Sorry about the size of the fonts in this, but basically everything we do can be put into 4 different bins in the Office of Science Quality and Integrity. There's a broad area of education and development, and that's where the Mendenhall program resides. The Emeritus program is also under this bin, as well as a number of different educational activities. You may have had NAGT summer students to come with you, and a variety of other youth programs that the USGS has, and a very busy part of our organization. Then there's a whole another bin called Evaluation and Review. This is where the research grade scientists that are evaluated, the entire orchestration of that is run through the RGEG office of OSCE, or Office of Science Quality and Integrity, including the examination periodically of our senior-most scientists and their eligibility for promotion to the ST grade. The bottom one in there is awards. This is something that we hope to be putting a lot more focus on. This is awards primarily from external entities, and I'll give you an example of one, I think, in the next slide or two. The third bin there is fundamental science practices, which is something that we've been following for any number of years. This is basically the way the USGS reviews and approves the science and the scientific products that are communicated either through internal USGS publications or through external publications. So it's basically the rule book of how to get your papers published, to put it in a succinct manner. In addition to that, there are some Office of Management and Budget and other external organizations requirements that we have to meet, and this is where OSCE is in the role of coordination. The last box in there is something that's very recent. We've added the USGS Ethics Office to the Office of Science Quality and Integrity. That's about an office of about 4 or 5 people that are charged to look at all aspects of ethics. This is scientific ethics as well as the broad area of ethics. If you've ever had any questions about, can I own a certain stock or a mutual fund, this is the group that you go to. Or if you were invited to be a lecturer and a professional society was going to foot the bill for that, what's a proper way to do it? Or if you're an adjunct professor somewhere and you were going to get some kind of a compensation of some type, what's the proper way to do that? So the Ethics Office is involved in helping us figure a lot of these things out, and I'll say it partly to keep us out of trouble. So some of our initial priorities in the Office of Science Quality and Integrity, things that have taken a lot of our energy so far in year one, include these things on these bullets here. The very first one was to really work very closely with the Department of Interior in helping them establish a policy for scientific integrity. USGS has been ahead of the curve relative to many agencies, science and technology agencies, as well as the department, in the sense that we've had a well-established policy of scientific integrity. That's Survey Manual, Chapter 525. I'm sure everybody knows about it in this room. But the department had not had a real formal policy of scientific integrity, and actually, over the last 2 years or so, a lot of effort's gone into this, and the USGS has been involved very heavily. And the department's integrity policy is really something that's getting a lot of good press in the Washington circles, and is viewed as a model in some respects, because it's very clear that the rules of the game to protect the integrity of science and scientific processes apply not only for those of us who are in Interior, who are in the science business, but also to every employee, including all political employees. So that's something that the DOI policy does. Second bullet there, making a number of things truly more bureau-wide. The Mendenhall program, as you will see, even before the creation of OSCE, is something that's been evolving over time to attract the interest of the entire spectrum of the science we do at the USGS. So in the old speak, the 4 science divisions, all of them had been participating for the last couple of years. But under OSCE, in the Office of the Director, we will be able to strengthen those efforts even more. I won't say a whole lot about Emeritus or RGEG or EDGE, and some of these others you can read yourself, and I'll be glad to talk to you more about the mission of the OSCE, while I'm here or in the future. Awards, one thing I wanted to call to your attention, some of you may be aware, USGS, we've been participating in the PCASE process for a couple of years now. PCASE stands for Presidential Early Career Award for Scientists and Engineers. And this is the highest civilian honor that can be bestowed by the U.S. government on young professionals in the early stages of their career. Typically for these kinds of awards, there's an age, qualification, but on the whole, the PCASE process allows agencies to set the rules of the game for themselves. So we have a nominal 5 years rule, pretty much, 5 years after the terminal degree or the 5 years after the terminal postdoc. And so we participated for the first time in the 2009 round, and we're eligible for 3 of these awards. Those slots are very, very carefully guarded by the Office of the President for the size of our agency, which is about $1 billion, so company 3 is pretty good. And so our first 3 awardees are listed there. One of them is sitting right here. I will embarrass her, Jean Hardenbeck, in case you didn't know. And then Nicholas Luco, some of you know, he's with the Geologic Hazards Science Center in Golden. And then Pam Nagler, whom I met for the first time at one of these colloquia 2 years ago, I think, maybe 3 years ago. Pam's with the Southwestern Biological Research Center, and she's in Tucson, Arizona. And if you're interested in learning about the work that Jean or Nico or Pam had done, you can go up and find out about that on the website. The 2010 nominees have been in the system for some time, and they've been telling us, this is the Office of the President, they've been telling us that the announcement is imminent at any time. So we're patiently waiting. We haven't been told that any of our nominees have been denied or kicked out yet. We don't think they will. So we expect to have good news, and we'll send some announcements out about the USGS awardees in year 2. And then the call for 2011 nominations we just sent out last week, and the deadline for nominations is September 9. The call includes the instructions on how to nominate people and the criteria and so on and so forth. So if you hadn't heard about this, and if you're not aware of it, you can get in touch with me and get in touch with your Senate Director as well as your Rex's office to learn more about the process, and I hope some of you will think about this further. Mendenhall program, FY11, this is the current fiscal year. We've had 22 join the survey. Those are the different locations of the different parts of the organization where postdocs have entered. We've had good funding this year. We've done very well. In FY11, virtually all projects were able to fund at pretty much requested level. We've covered pretty much all science areas of the USGS, and number count, and I keep count, we're approaching 200. I don't know if I'm doing this. I'm trying not to make the hiss. These are some of the projects for FY11 that we have funded. Some of them you may see here in the posters, and It's just a sampling of the kind of science, the range of science that's being done right now through this program. FY12, that's the year that's coming up. We're just about to complete the recruitment cycle for the FY12, and we think we'll have about 16 or 17 new postdocs coming in starting in October, which is smaller than in 11 or in previous years, but actually better than I expected it would be. It's been a transition year for us because we did become a new organization back in October because of the restructuring. We had a classical discipline-based organizational structure. We now have 6 mission areas that are organized around themes. We're all trying to figure out how to do a lot of things in the new and improved USGS. As you know, FY12 starts in October, and so the new postdocs will be arriving starting in October, and some may come as late as March. There are actually some that might come even later because the cycle, FY12 cycle, has been really protracted for a lot of different reasons. Partly it's a transition year, so there may actually be some coming in beyond March as an exception. Next, after that is FY13. The call for proposals just went out on Friday. This is the first time we're trying to do a call for proposals through a single call through your local friendly regional executives, and Jeff Kay is here in the back if you know him. If you don't, probably you should go and say hello to Jeff, because a lot of things do come through the Rex's offices, as well as the associate directors in the case of the Mendenhall. So I think some of you are aware of this and you've seen the call already, but if you haven't, go and ping your friendly center director. Deadline for proposals is 16th of September. Format and the process isn't going to be all that different, even though it's a transitional year. The individuals who may be involved in the review and selection process may be different, but fundamentally it will be the same parts of the organization, starting at the center, then the programs, then the mission area offices with input as well from Rex's too, as they choose. So we're hoping to get the program up in October, which is late for Mendenhall. Typically we get it up in July-ish, August timeframe. But we'll also try to add as much time as we can at the other end and try to keep the positions open for about 90 days, which is sort of a minimum open period in my book. And I want to say that the strong support for the program continues at all levels in the organization. As you all know, fiscal 12 and 13 could be somewhat difficult years that may require extra courage on many fronts, but the support for the program from every opportunity I get to ask people to articulate it continues to be quite strong. I'm going to view 12 as a transition year number 2 as we get used to the new organization and learn to do things under a new set of rules. So hopefully we learn those well. Where do the postdocs go? This is partly for some of you who are new scientists or new postdocs right now. I did a briefing, among many others, specifically to the new associate directors back in Reston, and they were kind of curious about what happens after 2 years. Well, actually, what happens after 2 years is there's many that are very enterprising and that stay on beyond the 2 years, and there are actually some that are very good at staying on to the full 4 years, which is a possibility in the kind of assignment that Mendenhalls arrive at the USGS with. Well, how did they do that? I'd be glad to talk to you about that during the poster session or sometime later in the evening even. What I tell everybody is if you're interested in longer-term USGS employment, start talking about that from day one. Let the system know, because opportunities that you seek may or may not be available at that center that you come into. USGS is a large organization. It's distributed all over the map, and so let the system and the people in the system know that you have longer-term interests. Mendenhall, in particular, doesn't confer any kind of a special status when it comes to permanent employment at the USGS. We've always kept it that way because we've always felt that competing for a permanent position at the survey through a national search type of an approach is best in your interest as well as in the interest of the survey. As of November 10, that's a snapshot of where people are heading post-Mendenhall. Not surprisingly, a good number go to universities. But this may be a surprise, but on the order of 50 to 60 usually somehow or other continue and stay on. And that 32 roughly permanent into U.S. jobs is on the order of 1 in 5, which is about where it stayed throughout the history of the program. So about 20% find a way to get a permanent position at the USGS. The other 80% who go on elsewhere and succeed, I'm as concerned, I'm as in communication with them, because I would like to pack the Supreme Court, no, not the Supreme Court, I'd like to pack the Academy of Sciences down the line with a large number of Mendenhalls, and I think that's a reachable goal. This is, again, perhaps the last slide, I think, something I shared with the associate directors, because some of them are very new to the associate director level jobs, and so the question comes up, how many Mendenhall fellows, and by extension really postdocs at the USGS, should we aspire to have each year? I'm calling them Mendenhall fellows here, but I mean all postdocs. That's not an easy number to get at the USGS. I've tried more than once to find out all across the USGS how many true postdocs really are there in the system. I still don't know the answer, but I do know how many Mendenhalls we've had. So if you say there are about 1,200 research scientists and every one of them aspires to have a postdoc every 5 years, we should have a stable number of about 240 every year in the USGS. In the 27 years of the USGS that I've been in, we've never had anything approaching that. So I try to be a little more modest in my goals and try to promote the idea that maybe we ought to go for at least 239 as a stable number. So anything you can do to promote that same concept, I would appreciate that. And then looking at it in terms of the dollars and investment, total amount of funds, I just threw up there $5 million for Mendenhalls, but if you say that there's at least that many other kinds of postdocs in the USGS system, 10 million, 15, I don't know, 20 million, that gives you an idea of the percentage that we are putting into this activity relative to our overall budget. It's rather small, but I think for a small investment, I'm biased, I think the investment results in some really wonderful results. So we're looking in the long run for stability and also opportunities for growth. I think they're going to be a little difficult in the coming year and the year after, but I plan to be here longer than that, and I'm an optimist fundamentally, and so we will keep trying to do what we can from OSCE and in Reston to find these opportunities for growth. There's some other things that I talked to the ADs about, associate directors about, and that's what I think of as untapped potential. You may have seen a Venn diagram starting, I don't know, last year that's being used by a number of managers that identifies areas of overlap among the 6 mission areas. And one of the things that I think I've heard several people, including our director, talk about is to capitalize on those areas where there's these intersections there. And I think this is one of the programs that could be a much bigger integrating agent from my perspective. And I think I'm hopeful that with the restructuring and my having dialogue and others having dialogue with all the associate directors and all of the regional executives, that we will try to capitalize more on this program and similar things as these integrating agents to pursue more work that's in those areas of overlap. Certainly it's a great way to bring in for 2-year term appointments the cream of the crop. We have no difficulty in attracting some of the best new graduates in a very wide range of fields. I mean, at one time when we talk about geology, because geology has been using Mendenhall for a long time, well, we've run this now for all parts of the scientific activities of the survey, and I have no doubt, looking at the quality of applicants, that we do attract and will continue to attract the best and the brightest. The survey is a magnet. A specific idea that a number of people have thrown around, including some in this room, is to look for areas of overlap. As an example, I just point out biology, and I know that there's no strong biology presence on the center here, nor is there in the Denver Federal Center or in Reston. So I have suggested and pleaded with powers that be in the biology side. That's maybe something to consider. And as a pilot for that, maybe have a few postdocs of some flavor or the other that are focused on biological science as well as other kinds of science that are done here, Reston and Denver. So we'll see where those ideas go. So I think that's it. Let me stop and see if there's a question or two. If not, that's fine too. We can move on to the next part of the program. Thank you.
Does the proportion of Mendenhalls reflect the overall proportion of research scientists in the organization? 12 in geology and
I don't think so, not at all. It's partly, the level of maturity of the program. In the geology side of the organization, we've been at it for a decade plus. Other parts of the organization have not. In this activity, it's not that they don't know about hiring new PhDs or something, but it's a question of investment and how do you choose to make the investment. I think as people get to know more and more about the individuals that do work through the Mendenhall program and the quality of science that's coming out of the Mendenhall effort, I think it's going to increase with time. Jake.
Jake, can you use the microphone? Sorry. We're going to ask today that anyone who has questions, please speak in the microphone because we are streaming this live.
Rama.
Go ahead.
Yeah, that question raised another question, and previously it would have been that meant that the geology division was providing more funds for the program, but now we have these different mission areas, so I guess I'm interested in how are we funding it, and actually is it that just geology is being more proactive in putting in proposals and so they're getting more than the funding, or is the number of successful postdocs still correlated with the amount of money coming in from some source?
Through FY11, it's been funded in the old way, in the sense that 11 was a transitional year, and so we made agreements that the way the geology part of it would be funded is in the same as before. All the programs that we used to call geology contributed proportional amounts, proportional to the size of that individual program. For FY12 forward, we're very much in the process of working those kinds of things out. Because of the necessity of the long lead time for advertising the positions and soliciting applications and doing the review, making the offers and all of that, we can't really wait to have all that nailed before going forward. But the expectation is, and what's been articulated consistently, is that all mission areas will contribute and will participate. And so in that sense, when we use the term truly bureau-wide, it's going to be bureau-wide funding. The details of how much and how we do that, that's the transition year comment that I made. We're all gradually figuring out how best to do that. And I think it's going to be a function also of the result of the call for proposals. Believe me, there were any number of people who were warning me about the not a high level of wisdom in sending a bureau-wide call for something like this. And I said, we have to. We have to do that. If we do get a large response and we get a large number of proposals, I think that's a message that one needs to pay attention to. After that, then, do we have the resources to immediately grow is something that collectively I think the mission areas will have to look at, and as well as others, not only the mission areas, but if you use the old model, the mission areas are the ones that have the large chunks of funds to, and responsible for large chunks of funds. So stay tuned. Okay, I'm here rest of the day. Can we have the panel members please come on up and maybe we can move on to the panel discussion. Well, let's see. How about the mentors sit on one side and the postdocs sit on the other side, and then Jean right in the middle? So she can pretend to be one or the other rather well, actually. So. See, I think Mike asked that I introduce the panel members. Many of you know who they are, but I think I'll go ahead and do that and then step out of the way. They all have some insights and thoughts that they want to share with you, and then hopefully we have enough time for some dialogue between audience and the panel. So starting way over there, Crystal Ng, she's with the Geology and Geophysics Science Center. I'm assuming that you're Adam. How do I pronounce your last name?
Syed.
Adam Syed from San Diego, right? Okay, he's a new scientist there at the Water Science Center. Nancy Prouty next to him, and she's with the Pacific Coastal and Marine Group in Santa Cruz. And then we have a distinguished professor there in the blue, Noah Finnegan. He's a professor as well as a Mendenhall Fellow, UC Santa Cruz. Jean Hardebeck there next to Noah is from Earthquake Science Center. She's worn both hats. She's been a Mendenhall as well as a mentor for a Mendenhall Fellow, so that's what the future holds. And then next to her is Dave John from the, I guess still the Western Minerals Environmental Science Center for a few more months at least, right? At least for a month or two. Next to him is Jake Lowenstern from Volcano Science Center. He's been a mentor to many. And then last but not least, Jesse Lacey from the Pacific Coastal and Marine Science Center. I just gave them a few questions to sort of prompt some thoughts, but I'd like for them in whatever order to tell us a little bit about themselves and their experience in either having been a postdoc or new scientist, or maybe they still are, and or mentoring, and take it from there in any order you like.
Okay. I'll start. I'm David John with the Western Minerals and Environmental Science Center. I was a mentor to one Mendenhall who's now a permanent employee. We have another Mendenhall coming in January. And actually Joe Colgan, who was the previous Mendenhall, is the chief or head, whatever, research advisor for that position. I've been involved in a number of other proposals, several that were, or opportunities, several that were advertised and several that didn't make the cut. I'm a great proponent of the Mendenhall program. I think it has a lot of benefits, both to the postdocs, obviously, but also to the research advisors. It really is nice to add fresh blood and new ideas, and comes with a pot of funding, which if the research, the postdocs are generous, it really beefs up your research budget.
Send it down to one of them.
Respond.
Okay, I thought that sitting on the end, I wouldn't have to speak so early, but anyway, okay. So I am a Mendenhall postdoc now. I am a year and 8 months into it, and I guess one of the questions that we were prompted with were what's some advice that we can give to new postdocs. And I guess thinking about it, I think that I would really encourage people to be really proactive about talking to people and seeking people out to talk to them. I think I found that starting my postdoc, everything I knew about the research world was relative to how things worked in a university, where everything's, the structure of, these hierarchical structures where you've got the, advisor at the top and postdocs and so forth. And so it's pretty easy to understand what anyone does as long as you know what group they're in and kind of what their status is. And that's not the way things work here. And so I realized that you don't just go to a research group's website to figure out who does the similar kind of things as you do or complementary things. And I think overall it's actually sort of a great thing that it's not these hierarchical structures. It just makes it a little bit more confusing to know what people do and how to find out what people do. But actually the great thing is that it pushes you to go out and actually talk to them. And so, I would just encourage you to realize early on that it's not going to be at your fingertips at your desk, at your computer. It's going to be a matter of getting out and talking to people to finding out about, what kind of science people are doing, and I think that's what leads to collaboration ideas and so forth. So I'll send this back down.
Well, there is a second mic there, right?
Okay, I'm Jake Lowenstern. I'm in the Volcano Science Center. I've been working here in Menlo Park for almost 19 years now. I did start out as a postdoc, though we didn't have Mendenhalls at the time. And there was sort of a death zone of years between when I came and when the survey perked up and started a new postdoc period, or started hiring postdocs again. There was probably almost 10 years where I was like the youngest person on campus, and it was very, very long time before things started to change. But now actually it's remarkable how many young people are around, or younger people are around on campus, and it's part of it is due to the Mendenhall program, part of it is due to the general overturn, but I think the Mendenhall program has been fantastic. I've been involved probably in 6 or 7 at least proposals to get Mendenhalls over the years. I've been in ones that we got rejected on. I've been on, in the very first level. I've been on ones where we've made it through to the very end and didn't get our person. I've been on ones where we got somebody, and everything in between. It seems this year we've got 2 postdocs coming in actually to work on Yellowstone, which is where I do a lot of my work. One of them is a Mendenhall, and one of them actually is coming with her own money from the United Kingdom to work with us, and so we're very excited about that. If I could generalize on a few things, I think one important thing for USGS people to do in setting up postdocs is to try and put together a proposal in that one-page proposal that we put together that is of interest to the science strategy, not something that people are going to kind of look at and wonder, well, who cares about that? You need to make it a topic that anybody anywhere in the survey could look at and say, yeah, I can see why the survey should be doing that. A second is to think a little bit strategically on who and how and where the person can best be situated. And an example this last year is that I was one of 4 advisors for a proposal to do remote sensing. And I was the one who kick-started it, but in the end we decided that by far the best place to put the person was with an advisor who knew something about remote sensing, in this case at the Astro team, or Astro Science Center in Flagstaff. And that was advantageous not just because the person ended up with the best mentor in terms of the science that he was doing, but also because astrogeology had never had a Mendenhall before. And that's kind of one of those little things that I wasn't on the panel to figure out what happened, but I imagine that was an advantage to this particular proposal, and that people are looking at it, and there could be a science center director there who said, hey, we've never had one of those before, and that might have helped it.
It's just a darn good proposal.
What's that?
It's just a darn good proposal.
No, okay, well, it was a good one. He's doing a great job, too. And then the last thing that I'll mention, sort of from the mentoring standpoint, is that the USGS, and this is similar to what Crystal was just saying, that USGS, for people coming in, is a sort of a bewildering institution, and even to us it is at this point, when we've got regions and we've got areas and we've got mission areas and mission area positions and divisions and disciplines, and everything gets very confusing, and there's a lot of rules, and there's a lot of way things get done. And so having somebody to kind of simplify it and to provide some wisdom on how to get things done is useful for people coming in. And in addition, sending them to the right people to get additional information for their individual project, because there's a lot of people out there. We tend to know more people than they do. There's a lot of people within the USGS who can get them resources to get things done. And so it's important for us to try to identify them and encourage them to talk to as many people as possible. That only not helps their project, but it also helps them when it comes time to choose positions and choose jobs. And the people who are known and the people who are trusted and who have made good impressions are the ones generally who are going to get hired. So, okay. Back down to you guys.
Well, I'll just follow up on Jake's, because maybe 2 years ago I was writing a paper on a coral project, and actually someone suggested going to talk to Jake because this was a project in Hawaii with volcanoes, and so here I was a coral oceanographer person going and talking to a volcanologist. But that was an example of sort of this idea that within the survey there's membership has its privileges, reaching out to this wide community of scientists, from biologists, geographers, geochemists. For me, that's been the greatest thing. I'm finishing my 4th year in my Mendenhall term and starting a new term, and I think that having this group of scientists that you can tap into has been really essential for the growth of my science. I just want to echo what Crystal was saying about really reaching out. At the end of my 2nd year, or actually the end of my 1st year, I signed up to be involved with the USGS Mentor program and was mentoring. We got teamed up with Matt Larson, so went out to Reston and gave a talk, and I think that really helped me reach out to the broader community and helped me get involved in some other projects beyond coastal marine geology. So I'd encourage people to look into that program as well. I think one of the questions that Rama asked us is what remains a mystery to you about the USGS, and I'd have to say the finance structure. And I'm sure I'm not alone in this, you know, get your money in July, spend it by August 1st kind of thing. And the other thing is GovTrip. I think every 2 weeks I get a note that I've done it wrong after 4 years. So hopefully another 4 years I'll learn that. But I think, yeah, the keys I think are really branching out, going in and talk to people and sort of selling yourself by going out and giving talks, whether it's within the USGS or at conferences, of course.
Say something. I'm Noah Finnegan again, and I guess I'm here, maybe partially Rama asked me to be here because I'm a unique, maybe test case for the Mendenhall program, in that I got a faculty job at the same time as a Mendenhall, and we were able to make it work so that I could do both, and that's meant that over the last 2 summers I've worked with Kevin Schmidt in landslide hazards on using remote sensing techniques on landslide detection. And so for me, the Mendenhall, I think, has been great because it has really helped to facilitate bridging my world at UC Santa Cruz with people both here in Menlo and to some extent at the USGS in Santa Cruz, although to a lesser extent. And so that, for me, that has been great, and I think it's been pretty synergistic, and I think there's a lot more potential there because the Mendenhall program is bringing people typically in from universities who are still retaining ties, who are working on new and interesting techniques and problems, and I think, if anything, you know, do more of this, because for me, you know, it's I look forward to an ongoing collaboration even after this term ends, and you know, you can get in the ivory tower where people kind of drill in on their little thing that they work on, and one of the refreshing things about interacting with people at the survey is that there is more of a sense of a constituency to which you're serving, and that's for me really refreshing, and I enjoy that aspect of being involved with the survey. So I'll leave it at there now.
Okay, so I'm Jean Hardebeck with Earthquake Science Center, and so I started off as a Mendenhall postdoc here and then was able to get a permanent position. So I think I would like to reiterate some of the advice that's already been said, which is you really kind of do need to kind of take initiative, figure out who you want to talk to, go talk to them, because a lot of people here do tend to be somewhat in a rut, that they have their people they work with and their things they do. And actually I found from the other side now that having postdocs and students here actually really kind of helps energize me and gets me to talk to other people and things like that. So I think that this is something that kind of goes both ways, but really having the postdocs here really helps that sort of energy level and kind of level of the communication. I also like to reiterate what Rama said at the beginning, which is that if you are a postdoc and you are interested in a permanent job here, that is something that you probably should make sure that people realize from the beginning, and that's something that I did. And I think the other thing that I did that was helpful for me in getting a permanent position was that I didn't just sort of work on my project in isolation, that I tried to get involved in more of the sort of applied and practical side of the survey, which was actually kind of easy for me because during my postdoc tenure we had two fairly major earthquakes in California, the 2003 San Simeon earthquake, which was actually the only earthquake in California that caused any deaths in I think the last 15 years or something, and also the 2004 Parkfield earthquake. And even though I was sort of just here as a postdoc or whatever, I jumped in and tried to be sort of a useful part of the response to those earthquakes. And I think that's something that was really appreciated, and I think something that did give me kind of an edge up on getting a permanent job here. So then I have mentored sort of as the primary research advisor for one Mendenhall, and I'm now currently kind of a co-advisor for two other Mendenhalls. And so I feel like I'm still at the early stages of really learning how to be a good research advisor, and I think I'm learning a lot of how to be a good research advisor from my Mendenhall research advisor and from watching some of my co-advisors for the Mendenhalls. But I think one of the important things about being an advisor is a lot of people, by the time they're here and doing a postdoc, they know what they're doing. And you kind of just, for the most part, you can kind of just get out of their way and let them do their research. But you do need to, in some ways, kind of insulate them from a lot of the stuff that's going on in the survey, that they may not understand how anything's organized and how the money works or anything like that. And Rama does a great job of kind of protecting the Mendenhalls from having to worry about money. But it can also be your job as a mentor to make sure that they don't have to really worry about anything, that they can really just focus on getting their research done and focus on getting some publications and the sort of things they need on their CV to get a permanent job here or elsewhere when they leave.
I've heard more than once that reality hits after 2 or 3 years. So.
But reality what?
Hits after 2 or 3 years of being a postdoc. So.
I'm Jessie Lacey. I'm a physical oceanographer at the Pacific Marine Science Center in Santa Cruz. I'm currently advising a Mendenhall postdoc. And I started here 10 years ago as a postdoc. It was actually the first cycle of Mendenhalls which I applied to but was not selected. So, and somehow the team figured out how to hire me anyway. But I would say, and so first of all, I guess from the advisor point of view, the process of getting a Mendenhall is, I think everyone who's been involved would agree that it's quite a lot of time and effort. But I would agree with what others have said, that both the process of coming up with a proposal and then interacting with the applicants even before you have a postdoc, which of course is wonderful, that whole process is stimulating. I think makes you think about your own science, your own project differently, and provides just more interaction with that group of young scientists out there, which I found exciting. So I think it's a good process to be involved in. To the postdocs, I would say that I think that as a postdoc here, you're surrounded by a lot of people. You know, you're surrounded by research scientists, some people who are very involved in project management and budgets, and technicians who are doing different things than you. And so it's important to remember that as a postdoc, you're in kind of a special slot, and that what you need to do is in a fairly limited amount of time finish a project and publish some results. And you may see a lot of people around you who have perfectly successful careers at the survey who aren't necessarily prioritizing that the same way you need to, because they're spending time on project management, or they have different responsibilities. So you have both the privilege and the responsibility that you get to spend your time on science, and you need to do that. I guess I've seen some postdocs get distracted by the many other opportunities. And while it's really important to take advantage of some of those opportunities, you also have to keep a little discipline on what your own goals are.
I'm Adam Syed. I'm not involved in the Mendenhall program. Coming to this colloquium was the first time I've heard of this. However, at UCLA we have a strong connection with the San Diego Projects Office, and so that was sort of how I got involved. I started interning there a few years ago, and after a couple summers of working there, I got brought on as a SCEP, and then I later applied for the permanent position and got hired as a hydrologist. I'm still currently finishing a PhD at UCLA, so I have a pretty heavy workload. And so prioritizing is exactly sort of what I'm going through. I'm involved in several projects. So when I come in and when I sit down in the morning, it's what do I need to work on? What's the most important thing to start? Because you get you have to learn how to prioritize things efficiently. And as far as mysteries, again, the financial situation, that was on the top of my list, but also the avenues to pursue, whether or not to go with the research grade or the office situation, and the balance between the reports and the publications, and how to try to optimize your contribution. And yeah, I think that's about all I got.
I think everybody's gone through at least once, which is great. You can go more than once if you want, but if anybody has any comments or thoughts or questions, now would be a good time to start to do that. We have at least 2 people with microphones that are willing to walk.
Thanks for sharing with us. I have kind of a managery question. I know that it's important to have a good relationship with the mentor of the Mendenhall postdoc. How much time have you been spending with your mentors? And does that change over the course of the postdoc? Do they unlock the door and say, go to it, or are they really spending a lot of time helping you through the research process?
That's you guys.
I'm in a unique position because I'm being mentored by Kevin, and I'm also mentoring graduate students, so I can see it from 2 sides. And I would say Kevin's doing a great job in providing me with enough background to understand the problem, but giving me enough space to kind of flail around. Because we're trying to do something new that may or may not work, and it's just a fundamentally trial and error process. And I think Kevin recognizes that process. So he's been there to give me the background, the advice I need, but has been, I would say, very relaxed about letting me explore, which I think is what needs to happen with a postdoc. I think, does a better job than I do as an advisor to my students, put it that way.
Yeah, I think probably depends on how much expertise you're bringing in terms of how much hand-holding will your mentor do. But I worked with Mike Field, who is recently transitioning out, and I remember thinking, oh my gosh, how can I do it without him? And then realizing that he provided me a lot of guidance, but also independence, and that I could do it without him. And I think some of the things he provided or another valuable mentor provides are resources. If they don't know the answer, pointing you in the right direction or encouraging you to, go speak with someone or go to a meeting. So I think their job is twofold, to sort of give you the independence so that you can do it once you leave the postdoctoral fellowship.
Okay. Yeah, I think I would echo a lot of what has been said. I think there's sort of a balance to be struck, and I'm sure it varies a lot, just, individual and individual. Everyone's got their different mentoring and postdoctoral style. I guess one thing I have noticed, at least with the Mendenhalls, it seems like it's been a way maybe to bring in sort of new ideas and maybe new tools or new approaches. So I think that, and I think I hear this from a number of other postdocs, you're not necessarily, what you're doing in your project is a lot of, what you put into the proposal. So it's not really like your mentor, that was his or her idea, and they are now hiring you to execute it. So, so I think as a result of that, there is a lot of independence and that the postdoc has. But I think at the same time, my mentor has been really great, and again, like letting me know like where I can find resources, and and being a sounding board for things. But I'm sure it does vary, just person to person.
I think at a university it's really common to bring in a postdoc and just kind of have them show up and say, okay, let's think of something cool to do. And I think what's really good about the Mendenhall program is that there is a lot of thought that goes into the proposal on both ends. And so I think a lot of that work is front-loaded so that you come in with a pretty well-constrained project. And I think you may get complaints about undoubtedly you do get complaints about the process, but from my perspective, and actually have a pretty long history of applying to the Mendenhall program, so I've done a number of applications, let's just leave it at that, more than 2. And
you worked hard.
I worked hard, and I did multiple applications in multiple years, so I've done this a bunch of times, and I think that there's no substitute for sitting down and reading the literature and getting your problem figured out before you start it. And so I think that that's a real advantage that this program has over a lot of university postdocs, where it's common to come in and kind of spend 6 months sort of trying to sort out what exactly you're even going to work on.
I mean, because we are mission directed or mission driven, we pretty much have to do that. The other thing is I've done any number of studies on this phase in the career of a scientist. And the one thing that's common to Academy of Sciences, NAS study after study, is clarity and definition. You've got to clearly define what it is you're going to hope to get out of it in that year or two, and vice versa for the institution. And if you do that, then it's going to succeed. So.
So as a Mendenhall Fellow, I guess I'm wondering how to extend the 2-year sweet deal into a 4-year sweet deal and to a permanent situation, because there's, I think, a million different ways to do it, and I just don't know anything at all about it.
Well, one way is to get yourself on projects outside of your immediate Mendenhall. In other words, try to focus the first 2 years on accomplishing at least part of what you said you were going to do, but expanding the scope of the work so it fits into existing projects or new projects where they'll put you in the staffing plan. Which may sound, I don't know if it sounds easier than it is or harder than it is, but it's ingraining yourself into other projects that are outside the funding of the Mendenhall program.
Yeah, I'm just trying to think of examples within our center of Mendenhalls who've been extended, and you know, first of all, your advisor needs to be an advocate for you. I mean, that's you need to have somebody who's the connection between you and the people with the money. And so one thing to do is to discuss it with your advisor about how would I go about getting additional funding, and can you see any ways, and sort of proceed from there. We've had people who are just doing such a cool project, and it's been advertised within our program, and the program coordinator recognizes that we don't want to have to cut it off after 2 years when the Mendenhall money runs out. We want to see this thing continue, whether or not we can hire the person. If we can just come up with another year's funding or another 2, that'll allow us to get a couple more publications out and have all the more interesting results. So part of it's within the program. A couple of years ago, we hired one of Gene's Mendenhalls, and we transferred the term over from the Mendenhall program in one sort of program into another program, because we recognized that somebody was really good, and we thought that person would make a great employee for ourselves, and that person is now permanent. So what you could learn out of that is that if there's sort of other projects out there, and this is sort of what Dave was saying, that you might be able to fit into, just start to make those connections so that people could see that you could contribute to their USGS research as well.
It's kind of a broad viewpoint, but now given the shift into the missionaries rather than the divisions, I think that is really beneficial, because you can then approach a group or a project and say, this is your topic that you're addressing, and you're really missing the paleo perspective or the geochemical perspective from it, because they're topic-based projects now. So I think that the transition that we're all sort of sitting in now was really beneficial in terms of approaching groups and saying, this is a niche that is missing in this question, and I have the competence.
So I just also wanted to say that, on the one hand, where you might be looking for places where you might fit in the survey and things that you might do to kind of integrate yourself into some sort of ongoing project or something, I think you also need to be making sure that you're really you're really building a CV with good solid publications, and that you're getting publications not just sort of in USGS publications, but publications in the sort of the peer-reviewed literature that for instance, if you were going to apply for faculty jobs, that would be, you would have a strong basis for applying to faculty jobs also, because although obviously quite a few people have been able to stay on after Mendenhall, it doesn't always work, and it might not really actually be the right thing. So I think you shouldn't be kind of limiting yourself to just trying to figure out what's the best way that I can make sure that I'm valuable to someone somewhere in the survey. I think you also need to make sure that you have a more sort of general, broad value as a scientist, so you can go out and you can apply for faculty jobs if that's sort of the way things take you, or apply for a research scientist job somewhere other than the survey.
Another avenue that I know a number of people have used, and it depends very much on one's background, on the kind of science that you do, and the culture of the science center where you are located. There are some science centers in the USGS where they generate a lot of money from reimbursable sources of funding, and there have been any number of Mendenhalls who figured that out quickly because they were in that culture. And they got involved in writing joint proposals in the first few months where they are, and the proposals are funded by other federal agencies, they're funded by nonprofits, they're funded by sister agencies in the Department of Interior, a number of different sources. And so I've known a number of Mendenhalls, by the time they got to their 3rd year, they had enough money to cover themselves. Not only that, but to also hire extra help. So those avenues are possible. It doesn't mean that it's going to work out in every case, but depending on the kind of work you do, that's something to explore.
I was going to make that same point, and I think, in fact, in our center that I mean, it's almost getting to the point where bringing in some funding is really almost a prerequisite for being considered for employment later on.
So I'll just repeat what I said in the beginning, which is talk to people. So I am going to be, coming up at the end of my Mendenhall, but fortunately I was able to find a project to continue on for a couple more years. But it's actually, so I'm in geology, geophysics now, but I actually managed to find a project in water resources. And so, and that really came about just by trying to talk to anybody who would listen to me. And what I've found here is people are actually incredibly open. So, they might not actually have a project, but they'll at least, like, they'll listen to, you telling them what kinds of things you're interested in. And people have been really great, even if they don't have any, solid leads for me, but maybe I can talk with somebody else. And so just really talking to people.
We can make them sit another 15, 20 minutes and I'll just look at them, but maybe not. So there's a question back there. So
I'm a new scientist in Okay. Not in the postdoc domain. I'm curious to hear how other disciplines, I'm not sure I'm using the correct terms here, disciplines or groups or whatever, sort of manage what I anticipate goes on in all of the horse trading with funds that you have. Is this sort of you meet each other in the hallway and, for example, you said, maybe I need some geochemical work. Do people sort of take that on for you and you don't actually have to transfer funds group to group, or is there actually sort of real horse trading that goes on? Is that a clear enough question?
In our team, we have these big projects, and people work on different projects. If you need a geochemist on your project, you will talk to the geochemist in your office, and they might just have a couple pay periods on your project for that 1 year. And it's not, people don't have, I know it's not the same as this in other parts of the survey, but in our part, people don't have these strong affiliations that you're on this project forever or that all your time is on this project. It's much more adjustable according to what each project is doing in each year, and so that's how we work it out. And then so then that means that gets worked out during the basis process, and then you don't have to do a lot of complicated transferring of funds afterwards.
Yeah, I'd just say there's no easy answer to that one because everybody works a little differently, and especially with the legacy of our 4 divisions, there's different business models. They're trying to break that down over time, but it's not really broken down at this point. So there's lots of us out there that if we have, for example, an instrument or a technique, and it's not going to take 6 months of our time, we'll just do it, and you just talk to them and they'll collaborate. If it's really going to take 6 months of time, then maybe you work it through the basis system. Sometimes you have to go outside the survey to get something done, and you'll have to raise some money to do that. So it depends on what and who.
I'd say the same thing, and I'm certainly open to spending a few hours or a few days working on something just to help people. But if it's going to cost me money outside of salary time, then it's a different story. And you try to put in the project, anticipate your needs, both for inside, if it's chemistry, for analysis either done inside the survey or sending them off to outside labs, and so you put money for operating expenses in your budget from year to year. I'm trying to anticipate that. But there's a lot of times you don't anticipate all your needs, and then you may get in the horse trading or the begging or some other scenario. And then you work with your contacts. I think it's probably very similar to the academic world, where you're making the best use of your networking and contacts.
I guess the positive thing that I hear in these answers is that there's a lot of freedom, there's a lot of latitude, and that in general, at least in my experience, I'm an optimist. The system didn't constrain me, and I went with ideas, and I go with ideas wherever there may be pots of money. And that's just, just a habit. And, just find people that you can help spend their money, Exhausted all questions? Looks like we have, and I guess that's okay. You're the...
Well, since I'm holding a microphone, I actually came up with a question that I would like to answer. What are your thoughts about? Okay. So, one of the things that I find that I'm needing to balance the projects that I'm working on, and I was curious to get the postdocs and recent postdocs' viewpoint on how one goes about setting that balance, particularly in regards to something like our Mendenhall proposal sort of workloads, and then all those other things that seem like a really fun thing to try. So any thoughts that you guys could share with the current postdocs in the audience? That would be very enlightening, I think.
Well, I think probably it's obvious, but really talk to your mentor. For example, my Mendenhall was to do coral reef studies in Hawaii, and then I got involved in some deep sea corals in the Gulf of Mexico. So I think talking to my advisor and saying, can I spend 40% or 20% of the time on this? There was lag between Molokai samples being in the queue where I had time to then do the deep sea stuff. But also knowing that contribution towards the other project would help your career, and communicating that clearly with your mentor. So I would say, and you probably know that, Jason, is just really, talk to your mentor and make sure you guys are both on the same page.
Separate from that, there have been, some really interesting opportunities that someone who's here in a postdoc assignment has gotten. Suddenly, there's an expedition to the Antarctic, or, DSDP leg, or, going off to the North Pole to do something. If these things are within some bounds, there is a lot of freedom that we try to offer here. And bottom line is, if you're getting your promised work for 2 years done, there's a lot of latitude from my perspective, but it's usually something that you do on a negotiated basis.
Yeah, and I think the key point here is doing things that are good for your career, because if you're only here for 2 years or 4 years and you need to come out with, a good solid set of publications to look for a job, that really needs to take, what's good for the postdoc's career really needs to take precedence over, in my mind, and maybe not everybody agrees with this, over, first of all, what would be fun, secondly, what the survey needs to get out of you, and I would even say getting done exactly what you said in your proposal you were going to get done. Because if you find something much more interesting than the thing you were after in that proposal, that becomes more important for you, more important for survey, and more important for science to kind of go after that other thing.
Well, thank you very much, all of you, for taking time off in your busy days, no doubt, and sharing your views on survey experience. And I guess we have the poster session starting at 2:30, is that right?
Talks.
Talks, okay. Individual talks, right. Thank you.
So the next part of our program is the brief presentations by the 14 new USGS scientists today. If possible, I would like to hold questions until the end during the poster session. So with that, I'm going to go ahead and introduce Jane Zelikova. She's from the USGS Southwest Biological Science Center in Moab. And she's here today to talk a bit about carbon cycling on the Colorado Plateau.
Okay. Holy crap. All right. Hi. Really excited to be here. It's actually really great for me to have a chance to come meet all of you and get to hear about what you do, because as we were just discussing, I think I'm the only biology division, whatever we call it these days, person here. So I work in Moab, Utah, but actually I'm housed at the University of Colorado, which is in Boulder, and I work with Dr. Nicole Barger at University of Colorado, and also Sasha Reed, who is a new scientist, a new USGS scientist in Moab. And if you haven't checked out her work, she's really awesome, and she does really cool stuff. So the project that I propose to do as a Mendenhall Fellow, and that I'm basically almost a year into, is looking at how regional climate change on the Colorado Plateau interacts with land use change, specifically grazing and other types of land use that we see in the Southwest, and how those things together impact carbon cycling. And so this is kind of a conceptual diagram to illustrate in a lot of boxes and arrows way what I'm interested in. And clearly the biological portion of the biogeochemical and especially carbon cycle is really important. And as a biologist, I think a lot about what the biosphere, how the biosphere interacts with the atmosphere and how that impacts carbon. And so I highlighted in red all the different boxes that I am particularly interested in. And there are very few boxes that are not highlighted. And as I look at them now, I actually think that probably I am also interested in the other ones. And there's really very little that I'm not interested in when I'm thinking about biology. And carbon is just one of the things that I'm particularly excited to think about, because it's such an important thing that we as biologists are dealing with right now in terms of climate change. But really, I'm also interested in the critters and the plants and in the dirt itself. I really like playing with dirt, and so this is my chance to do that as a job. And so the things that I'm measuring as part of my Mendenhall are really thinking about how soil community structure and activity are impacted by changes in land use. So particularly with grazing, and especially in the Southwest, grazing is impacting a lot of the vegetation and also impacting, causing a lot of erosion, soil erosion, and so that's really impacting the amount of carbon that's in the soil and potential for carbon storage. But also I'm interested in changes in plant community structure, woody encroachment, the spread of invasive species. Particularly lately I've been thinking about cheatgrass a lot. As I find it embedded in my shoes, I start thinking about what I'm doing as a seed dispersal vector in moving cheatgrass around the world. But I'm also thinking about the feedbacks from the soil back into the atmosphere, and so how climate change might be impacting microbial communities and changing microbial communities and potentially changing soil respiration. And so those are the things that I'm going to be measuring, and currently I'm measuring as a Mendenhall. That's a lot of stuff to measure. So instead of measuring everything all at once, I've kind of developed a two-prong approach to this. And the first thing is doing a regional assessment across the Colorado Plateau, specifically working in Utah, the southeastern part of Utah, and looking at how land use, and particularly grazing, is impacting both above and below ground carbon stocks. And so what we've been doing since April of this year is going across, really there's 1,000 different exclosures that have been maintained by the BLM and the Forest Service that have been put up since the 1950s and have excluded grazers, livestock and wildlife grazers. And so we've been going into a lot of those exclosures and looking at and actually measuring above ground soil carbon and soil, above ground and below ground carbon, both. And so now we're sitting on literally a ton of soil that I will be analyzing for the next year and thinking about how much carbon there is. But also coupled with that, I proposed and I will be carrying out next summer a soil transplant experiment, which is going to be taking soils from inside and outside of those long-term exclosures and moving them down in elevational gradient, and basically taking those soils and putting them in conditions of warmer climate with fewer precipitation events or smaller precipitation events. And so I'll be measuring soil respiration, looking at soil nutrient dynamics, and also hoping that I can get some money and start looking at microbial community changes as climate changes and as land use is imposed on that landscape. So that's my Mendenhall project, and I am definitely interested in working at the USGS. So since this is something I'm supposed to talk about, I love working at the USGS. It's been a really amazing experience. I've loved every single person I've interacted with so far, and I look for opportunities to stay for longer. Just saying, if you know something, let me know. I'll be sitting over there. That's it. Thanks.
So while I'm queuing up the next presentation, we'll be hearing from Michael Marshall. Come on down. For those of you in the audience that would like to know the order that we're doing our presentations, it's actually on the second page of the abstract volume in the back. All right. So Michael's coming to us from the from the USGS Western Geographic Science Center in Flagstaff.
Hi, everybody. Yeah, as you can see, the title of my project is Mapping Water Productivity in the Central Valley. Kind of weird. I'm based in Flagstaff, but all my work is out here. I'm with Prasad Thinkabel out there. And for the rest of the talk, water productivity will be defined as the ratio of crop yield, or biomass, to evapotranspiration. This picture here is taken from Twitchell Island, which is out in the Delta, and I like it because it's probably the most extravagant use of water that I've seen for irrigation in my travels across the Central Valley. These huge pumps draw water from the river over these levees into rice fields on Twitchell Island. Irrigated agriculture is an important issue in California. It represents about 80% of the annual water budget, and a lot of it, it's debated, is misused, right? So these are kind of my objectives. Basically, I'm using hyperspectral and spatial remote sensing data to get at water productivity for agricultural irrigated crops over California. And the two components that we look at are biomass and evapotranspiration. And so this involves ground data collection and calibration of satellite data over the next couple of years. And let's see here. We're also, as I said, determining water productivity. It's what are the factors contributing to it, such as soil salinity tends to lower water production. And then, of course, what we are ultimately looking at is how much water can be saved and putting a monetary value on it. Like, if we lower soil salinity by so much, like, how much water will that save? And that's really important to farmers. They want to know, you know, some farmers in the South in particular spend as much as $700 per acre foot for water. So if we can actually provide them with solutions, they're more than willing to try them. So this is a diagram of the study area. The red boxes represent Landsat coverage. The black boxes represent 10 by 10 kilometer area, which I use to access like higher resolution data, Hyperion, Iconos, QuickBird, and so forth. And you can see we cover quite a bit of the Central Valley. Our field visits usually take about a month. I just got back from my second one a couple of days ago. We cover places as far north as Oroville and as far south as Wasco, California, which is just outside of Bakersfield. And we're collecting for corn, cotton, rice, and alfalfa. Those are the big water wasters in California. And our primary interest is collecting field spectra, which we'll use to calibrate the hyperspectral data. And we're going to get about, well, I should say over 3,000 points over this summer, and then next summer, hopefully, as much. And this is basically just kind of an outline of the parameters we're collecting. I don't have results as yet. Like I said, we're in our second visit. We have one more visit this summer. That's my field assistant, Tony, with the field spec, standing above corn, which is now 3 meters high. So we're in it instead of over it. And we're collecting other parameters such as PAR, LAI, wet biomass, And so we'll use that data to estimate biomass and then extrapolate using the satellite data. And then, of course, the other big parameter is evapotranspiration, which was my dissertation topic, but I'm collaborating with folks at USDA, UC Davis, and the California Department of Water Resources to get that data. So we just happen to be collecting the biomass on fields which evapotranspiration is being collected as well. And then, of course, with this data, we can look at the contributing factors and do our sensitivity analysis. And then finally, this is kind of where I see the project helping and kind of where it will help not only USGS but scientists in the field. I think most importantly for me, since most of my work has been in the developing world and Prasad as well, is we'd like to use these models to help countries where water is a much more important issue, such as Somalia, where you've probably seen a lot of footage of the famine and drought there. So that's basically a summary of the work. And I'm sorry, I'm really tired. I just flew from Flagstaff, but that pretty much sums it up, what I've done so far.
Our next speaker will be Joel Sankey. And Joel is joining us from the Western Geographic Science Center in Tucson. There's a timer just to the left. You'll have 5 minutes.
Yeah, so I'm Joel Sankey, and I'm affiliated with the Western Geographic Science Center based down in Tucson. I'm also affiliated with the National Phenology Network. And my research focuses on the interactions and climate change effects on wildfire, vegetation phenology, and then dust, big dust storms and post-fire dust emissions. My research all really centers on the fact that wildfire regimes are changing around the world, and in the western U.S., fire regimes are changing specifically with an increase in the length of the annual fire season, an increase of the number of big fires that we see each year, as well as just an increase in the number of fires per year, wildfire frequency. My research really centers on fire effects on soils, and I evaluate the effectiveness of common post-fire restoration or rehabilitation treatments that cost quite a bit of money and are intended to stabilize the soil surface after fires. And then I really focus as well, or even more specifically, on stabilization of soil surfaces that are prone to these really big dust events and dust storms that blow off of burned rangelands and shrublands throughout the western U.S., and I have an emphasis in shrublands of the Great Basin specifically. But my research also just fits into kind of this broader scale work by university and federal scientists looking at kind of these regional scale implications and interactions of enhanced dust emissions, changes in the regional climate, as well as perturbations of the hydrologic regimes and phenology as well, both in lowland deserts and then downwind mountain ranges. So the primary question that I'm addressing with my Mendenhall Fellowship project is to look at the impact of the increased length of the annual fire season on the amount of time that soils remain bare after fires and are prone to these big dust storms and big disturbance events. There's a paradigm in places like the Great Basin where you have a seasonal climate that after a summer fire, soils tend to remain bare throughout the fall and winter dormant seasons and then green up in the subsequent spring. However, with an increase in the length of the fire season, we might expect, for example, that with more early season fires, we'd see an increased window of time that soils remain bare, and I'm essentially evaluating the length or that period of time post-fire that soils are bare using remote sensing phenology or phenometrics. Conversely, with more late season fires, we might expect shorter windows of time that soils are bare and prone to these big dust events. And then in general, there's a question of whether post-fire soil stabilization varies as a function of fire date, so the time of the year that fires burn, as well as restoration treatments that are performed on these surfaces, as well as obviously just seasonal climate effects as well. So that's what I'm working on, and I've got a poster over there that actually has results and methods if you want to see some of that more specifically. And thank you very much.
So now we're going to change gears a little bit, and we're going to move over into the realm of toxic metal geochemistry. And I'd like to go ahead and introduce Sarah Hayes from our office here in Menlo Park. And Sarah's with the Western Mineral and Environmental Resources Group.
All right, I study tellurium, and probably you guys have never heard of tellurium, but it's on the periodic table. And why you should care about it is because it's used in cadmium telluride-based solar panels, and that's definitely of growing importance to all of us. But it's also toxic. It's right underneath selenium, and so selenium's also toxic. And so we'd like to know more about it before we start using it in large-scale solar farms, which transports lots of tellurium into populated areas. But we don't know very much about tellurium because it's relatively rare, and so we didn't think it was that important. We just assumed that it behaved like selenium, and okay, well, that's close enough. But now it's time to learn more. So my project is specifically looking at what the affinity of tellurium for iron oxides to see if it's similar to selenium, in that selenium has a strong affinity. And we use X-ray absorption spectroscopy, which is the top right graph, to look at the bonding structure of the absorption complex. And we also, the other part of my project is to look at how tellurium behaves in the natural environment. So it does what we're looking at in the lab, the simplified version of what we're looking at in the lab. Does that actually translate to the field? So we use, I'm doing some laboratory absorption experiments, and also using X-ray absorption spectroscopy to look at the absorption complex geometry. And then also, I'm also using X-ray absorption spectroscopy to look at the natural samples and all their microfocus techniques to try to make the link between laboratory and the field. So what we've learned so far is that tellurium, tellurite and tellurate, which are environmentally relevant species, both have a strong affinity for iron oxides, but that there are actually some differences from selenium. And I have more to show you at my poster. And also, we have started to look at natural samples, and so we're able to use these techniques basically. I found tellurium bismuth phase predominates in the first sample that I've looked at, but we also see that the tellurium is oxidizing, and so we'd like to know more about how that's happening. Is it a surface coating, or is it being mobilized, and how mobile is it in the environment? And so if you want to know more, you can come and see my poster. I guess that was really short, wasn't it? Oh, well.
All right, so we're going to switch gears yet again over into a loose grouping of modern sediment transport studies. And we'll start with J. Toby Minier from the USGS California Water Science Center in Sacramento.
All right, great. Thanks, Jason. This is a project I've been working on with Scott Wright up at the Sacramento Water Science Center. And I think the title is kind of nice because, Jason was proposing this. He said, pick something that's sort of representative of what you do in your research, and I think this title kind of sums it up. I'm mostly a modern geomorphologist, but I like to take the big picture into view, and particularly human impacts on the modern environment is what I like to work on. So, modern geomorphology in a post-glacial landscape and implications for river restoration in Yosemite National Park. Let's see, I guess this is the just general overview. This is a project that's just the first phase, which I'll describe in a little bit, is just summing up, and we're moving into a second phase. It's been a very short timeline. It's been about maybe 6 months, and we're in review for the scientific investigations report, so I'm kind of proud about that, although slightly more sleep deprived because of it. The general location map here is on the left, and this is the watershed for Yosemite Valley, and you can see there's a little white box in the middle there. That's the project site, which is blown up on the right, and this is just a hybrid DEM that we've come up with. And essentially the problem here is that there are a number of undersized bridges, potentially undersized bridges, that are historically built in this reach, and the Park Service is really interested in figuring out what effects that has on the local geomorphology and hydraulics around the bridges. I chose this. I mostly highlighted methods in this talk just to give you sort of a flavor of what I like to do. And that sort of generally falls into 3 types: the field measurements, numerical modeling, and desktop analyses. In terms of the topographic surveys, I think one of the unique things, well, I guess not so unique these days, a lot of people are starting in on it, but one thing that I've spent several years working on is ground-based LiDAR, which the instrument is shown in the upper panel there. And essentially is just it's a laser-based system that measures points in a real-world environment, and then we can use that to reconstruct a full 3-dimensional image of a sometimes very complex natural environment. And down below you can see that's the one panel of the returns showing a side view through some riparian forest and with some conifers in the background. And then you can see in the sort of middle section there's actually a bridge that we're looking through and a road berm. I guess we don't have a pointer, but hopefully you can see that. Oh, I can use the mouse. There it is. There's the road berm, and there's the bridge. So it's a very handy tool. And basically we combined some of the ground-based LiDAR with a bathymetric survey and aerial LiDAR to create this really fine-scale hybrid mesh surface, and then basically use some geomorphic mapping and some measurements of grain size to come up with a numerical model. This is the old MD SWIMS, now IRIC version, which is the USGS 2D hydrodynamic model. And we basically tested out a variety of different scenarios. I guess I could highlight some of the results. This is provisional, I guess I should say. But there are more results on the poster over there, if you want to see those. Sort of the interesting things are that basically that it tends to be higher velocities around the bridges and higher relative to historical velocities. So that's sort of our phase 1, and then basically our phase 2 is moving on to this broader scale context of what geomorphology is doing, or what the geomorphic influences are for this reach of the Merced. And I think this is all very preliminary, I should say. This is probably the most prepared I've ever been for AGU. I've got a poster, I was blown away. So one of the things that has come out of that is that basically there are 3 main drainages that go into the upper Merced, and this really hasn't been articulated well, at least by most other folks. And Tenaya Creek and Upper Merced have both been glaciated in the last glacial maximum. But Illilouette Creek, the southern drainage, was not well glaciated for some interesting reasons. And the interesting part about that is that the long profile for Tenaya Creek and Merced are basically a series of steps where you have these old glacial lakes and now valleys that create big sediment sinks, whereas Illilouette Creek has basically none of that. It has basically a very continuous, very steep profile. And the interesting part about that is that, so essentially the Tenaya Creek and Upper Merced produce a lot of the water, but Illilouette Creek produces a lot of the sediment, so there's a very big disjunction there between the two, and related partly to the flood frequency of the different events. And then as part of this bigger geomorphic context study, we're looking quite a bit at the bed load and suspended load transport. Some interesting things I could pull out there, just that suspended load is very, very low. It's that low orange dotted line, and that the bed load is very, very high, because it's a very steep site. And so you end up getting this kind of interesting dynamic where you have very low sediment supply or suspended sediment and relatively higher bed load. And since it's getting kind of late in the day, I thought it'd be kind of fun to show you a video. I kind of like videos personally, if I can find the mouse. What I'll show you here, this is the shaded relief map of the hybrid surface. So that's using ground-based aerial in the floodplains, ground-based around the banks, and in some of the bars, and then bathymetry for the underwater surface. And I'm just going to overlay some of the ground-based LiDAR on top of that, including some of the bridges. Hopefully it'll work. It's a little pixelated. And sorry, the bridges aren't shown here. They're cut out. And we're going to throw in some ground-based LiDAR so you can see what that looks like. This is just a couple of scans. And we're working on trying to look at some of the floodplain roughnesses. It's really kind of interesting in this area with the conifers. You can pull that out of the ground-based. You're looking downstream. There's a series of trees that have fallen over in the channel, and then some stumps from the historical channel. And from that ground-based LiDAR, what was really helpful was to find out what the exact parameters of the bridges were, which they're quite complex bridges, as you'll see here. They have arches, they have pillars, they have footings, and all of that, trying to get that in a traditional survey sense is very difficult. They're very, very quick in a ground-based LiDAR situation. This took about 20 minutes to do that bridge. So other interesting things I'll be working on during this postdoc, we've got some really neat projects with the San Joaquin River Restoration Program, the Trinity River Restoration Program, and the Klamath Wrench Project, doing some temperature modeling, and then also with the Elwha River Dams Removal Project, which is starting on September 17th. And I thought I would have a shameless plug, is that the Coastal Marine Group, so John Warwick and Amy Drought and I are going up there in a couple weeks to go start surveying. The dams are coming out on the 17th, and we're hoping we have funding for the pre-project survey, but we don't have any funding for the post-project survey. So if anybody has any ideas or would like to get in touch with me about ground-based LiDAR, I'd be happy to talk about it. Thanks.
So our next talk will be by Maureen Downing-Kuntz, and she's also with the California Water Science Center in Sacramento.
Great. Well, thanks for having me up here. It's really awesome to be here. Much like Toby, I studied at Cal. I'm also now at the Sacramento Water Science Center. And in fact, my first semester at Berkeley, Toby was my GSI, my teaching assistant for my river restoration class. And I want you guys to know he was really awesome. I studied environmental fluid mechanics at Berkeley with Mark Stacy. And my project and my dissertation, I looked at the physical interactions between floating plants and the environmental flows. And now I'm in Sacramento. I'm working with Dave Scholhammer, and we're looking at suspended sediment dynamics in the tidal reach of bay tributaries. First, you need to know that sediment supply to the San Francisco Bay is important. This is for you out-of-towners. I have a satellite image of the bay, and you can see there's some coloration to the water, which is the suspended sediment. So you can see it's a very turbid estuary. The quantity of suspended sediment in the bay affects many environmental processes that we care about, including shoreline and intertidal habitat, contaminant transport, primary productivity of the waters, and also shipping ports and navigation. However, sediment supply to the San Francisco Bay is also changing. There's recent findings to demonstrate that suspended sediment supply from the Central Valley is decreasing over time, and so this implies that local tributaries of the bay are going to become relatively more important in supplying sediment to the bay. Sediment supply is monitored throughout some bay tributaries using sediment gauges that are located upstream of the tidal influence. And one key uncertainty with that is, do these upstream sediment gauges accurately estimate the sediment supply that's actually making it to the bay? And another way to ask that question would be, how do tidal reaches of these bay tributaries alter sediment supply? And so to answer this question, we're looking at sediment flux in Corte Madera Creek, which is a small watershed in Marin County. We have 2 gauging stations. One is located upstream of the tidal influence, and another sediment gauge is at the tidal at the mouth of the creek. And so most of the work we're going to do is just to compare sediment flux between these gauges at tidal and seasonal timescales, and then we can understand sediment dynamics in this tidal reach. This will support the development of predictive models of sediment transport, and it also will inform bay management decisions. I have a lot of data that I can share with you on my poster, which is outside, so please come see it, and thanks a lot.
So our next speaker will be Lissa McVean from the Pacific Coastal and Marine Science Center in Santa Cruz. And
Hi, I'm Lissa. I am also out of the same lab as Maureen, Mark Stacy's lab at UC Berkeley. And now I work with Jesse Lacey as a postdoc in the Pacific Coastal and Marine Science Center in Santa Cruz. So I will only work with people whose last names rhyme with Lacey and Stacy. And I am studying the dynamics of flow and sediment through an estuary. And kind of the catch-all question for me is how exactly does sediment cycle between estuarine habitats? And so I'm looking at very shallow habitats, mudflats specifically. Other people look at how sediment exchanges with the channels, between channels and shoals, et cetera. So this question can inform some really relevant ongoing work that's being worked on by a multitude of scientists right now, such as the viability of marsh restoration. So I have photos here of San Francisco Bay. I've worked in the 2 tips of San Francisco Bay, north and south. And there's a landscape scale marsh restoration currently underway. And also, this question can help inform the system's response to perturbations such as sea level rise. And it can help us parameterize really complicated processes to improve hydrodynamic and scalar transport models. Okay, so estuarine dynamics, as far as I am concerned with it, really encompasses hydrodynamics as well as sediment transport processes. And these 2 are constantly feeding back into one another. And the hydrodynamics are dominated by several forcing mechanisms, such as the tides that are sloshing back and forth. We have wind and waves imparting energy to the system, density gradients that form in every spatial dimension and change constantly. And then turbulence and mixing, which of course is responsible for lifting sediment up off the bottom into the water column where it can be transported. So the 2 obvious linkages between the sediment transport processes and the hydrodynamics are, of course, geomorphology, which, I mean, the shape of the estuary is the primary control on what's happening dynamically. And that changes on long time scales. But the water density can also be affected by concentrations of suspended sediment, and that changes on very short time scales. Okay, so we are using field measurements as well as idealized numerical modeling to get at a couple of more specific questions. Firstly, which processes dominate sediment transport in the very, very shallowest regions of an estuary? So I'm downstream of like what Maureen showed, but on the very shallow mudflats. So if you look at this photo on the right-hand side, that's one of our tripods on a dry mudflat. So it's completely intertidal. It dries on every tidal cycle. And obviously there was water when we deployed it. This photo was taken from a helicopter that I was not in, unfortunately. And on the left-hand side, we have a photo that has a little bit more water, but it was probably not enough for the boat that we had out there. So that leads to my second question, which is how exactly are flow and sediment dynamics affected by wetting and drying? And we think that drying on every tidal cycle affects both bed sediment properties as well as suspended sediment properties, and then of course how the water column is capable of transporting them. And as everyone else, I have results on my poster, and I would love to tell you more about it. And that's the end.
All right, so we're going to change gears yet again, and now we're going to move over to a brief talk about groundwater flow modeling from Adam Syed, at the California Water Science Center down in San Diego.
So this is a topic of one of the topics of my dissertation at UCLA. It's also closely related to a California Water Science Center research program grant that I received that I'll be working on next year. So in groundwater modeling, we often have complex subsurface geometries, and we have to then use observation data to estimate the parameters of the model. So I'm going to be talking today about parameter estimation, and this is a new algorithm that I developed. So it's based primarily on a concept called quasi-linearization. And this is essentially the basic flow diagram of the algorithm. So we start with an initial guess at our parameter, which could be hydraulic conductivity, which is represented by K. This gives us an estimate of the state of the system, which could be drawdown, for example. We then linearize the model using a Taylor series expansion. And then we solve the least squares problem as a linear regression problem. This results in an update on the parameter vector, which we then cycle back through. We set k naught equal to k1 unless we observe a very small difference. Okay, we say the algorithm is converged. Problem with this algorithm is that this particular regression problem, this is a quadratic programming problem, has been typically pretty large to solve, and having to do this several times makes it sort of defeat the purpose. So this research is focused on how to reduce the computational burden of this particular problem, which can be represented here as this system of equations. We use a method called proper orthogonal decomposition, or POD, that aims to project this model into a subspace. If you want to know more about it, I can explain it. Basically, this is a much smaller set of equations, several orders of magnitude smaller and much faster. And then we just import this into this linear regression problem, and this makes this a very trivial problem to solve. And so this speeds up the algorithm dramatically. And so this was applied to a two-dimensional finite element groundwater flow model in Italy. This is on the island of Sardinia. I just used the model grid. So this zonation pattern is completely hypothetical, and these wells are completely hypothetical. But basically, it has about 22,000 nodes, and I reduced it down to, say, 60 equations, for example, for the 7-zone case. You can get it down as low as 60 equations. So it solves much, much faster. So these are the results of the algorithm, and we found some interesting things. In order to project this model into a subspace, we have to evaluate the subspace, which requires computational expense. So and at each iteration of the algorithm, theoretically, we're supposed to do this in order to make the reduced model accurate. However, what if we don't do it? What if we just use as the basis from before and see if it works? It turns out it does work. It continues to converge, even so. And so this means that we don't need as much computational burden. We have a further reduction in computational burden because we only have to solve for that basis once at the very beginning of the algorithm. So this is a massive improvement on the current state of this algorithm. And so here we have these results. We have scenario 2 is where we update this reduced model space, and scenario 3 is where we don't. And we see that we don't see differences between the three algorithms until the objective gets very small, right? So essentially, there is no difference in the convergence. And in fact, if we add measurement noise, we actually see that, in fact, there is no difference. And in reality, we're going to have measurement noise. So therefore, we can say that in reality, this algorithm is just as good as the original quasi-linearization algorithm. And that's one major discovery that we found. Another major discovery we found is that by not updating that basis, by not updating this reduced space, we actually can improve on the stability of the algorithm. So for example, here in this 15-zone convergence case, we have a situation where a parameter hits its lower bound on iteration 1. This creates a constraint on how the quasi-linearization algorithm wants to proceed. And so as a result of that, the algorithm then later on, and the other parameters sort of compensate for this. This is a result of insensitivity. And so later on, the algorithm slows down its convergence because it has to then pick up that one parameter that it lost track of and bring it back up into it closer to its optimum before it achieves superlinear convergence. And we see that if we don't update the basis, in fact, it continues to converge superlinearly. And this is because the projection is based on the original parameter set that did not contain a parameter on its lower bound, therefore better conditioning the problem. So that's it.
All right, so now we're going to move over into the seismic and paleoseismic series of talks. And we're going to start with Karen Luttrell with the Volcano Science Center.
Do I have to do something to make it start? Okay. I'm Karen Luttrell. I am here at the Volcano Science Center here in Menlo Park. And so instead of trying to synthesize everything that I work on into a talk, what I actually decided to do was just, I actually have a poster and talk slides and an abstract on 3 non-overlapping subjects of my research, actually. I'm going to tell you a little bit about this problem here, but actually if you want to know, so the overarching theme of my Mendenhall project is to look at climate-related forcing of seismic and volcanic processes. So in my world, I view climate as a way to redistribute water mass. And water mass is heavy, and so I'm a solid Earth geophysicist. The Earth responds to that water mass, and also that water mass sinks in and can change a stress field via changing pore pressures and things like that. So if you want to talk to me more about sort of the spectrum of ways in which climate systems intersect tectonic systems, then talk to me about that later. Or also, on a completely unrelated note, if you want to talk to me more about sort of broader stress modeling of tectonic forces, you can talk to me about that too. But right now, I just thought I'd tell you about a project that a problem that I've been looking at for the last couple of weeks or so, based on some interesting data that we've seen from Yellowstone National Park. So this is the map here on the left. There it is. This is Yellowstone Lake. And so the yellow splotches are locations of plate boundary observatory boreholes that have some instruments in them. There are seismometers in all of them, but there are also some very sensitive instruments that measure deformation. There are strain meters and tilt meters, so specifically those measure the horizontal gradient of displacement. And essentially they're incredibly, incredibly sensitive instruments. So these were mostly installed around 2 years ago or so. So they're you know, it's an instrument that's more sensitive than anything we've had before, and we're just sort of starting to have enough of the data to start to go through and look and see what we can learn about the systems. So let's see. So this one in the middle here shows an example of a record from one of these strain meters. The most dominant thing that you see in it is the daily earth tide. So this is the solid earth tide, and that's this wiggle here, and we know a lot about that. So, and then ignore this guy here. That's the teleseismic arrival of an earthquake that was in Alaska. So ignore that. What we're actually interested in is the beginning of these wiggles right here. That's an interesting signal that we've been trying to learn more about. It shows up in the strain meter data, it shows up in the tilt meter data, and it also, interestingly enough, shows up in a completely unrelated instrument. That would be the stream discharge from the lake. So the working hypothesis here is that something is happening to the lake, and the lake levels maybe are changing, and we're seeing the solid Earth respond to this. Just a little bit about the characterization of this signal. It's a long period, and it's incredibly consistent. So the most dominant periods are 78 minutes and 55 minutes. So this is sort of longer than what you would expect from a Seiche wave or some kind of sort of other lake basin dynamic like that. So what we're looking at here is, here's again the sort of time series signal. Here's our wiggles, and here's another wiggle starting up. And then here, this is sort of a spectrogram of over 10 days, what is the sort of frequency component. And yeah, the frequency is incredibly consistent. And there are long periods, but there are also sort of shorter period signals that show up at the same time. Another interesting thing that, so these kinds of signals show up and are strongest in the summer, but they're present year-round. So here we're looking at sort of spectra. I apologize that these are not exactly the same time period nor exactly the same frequency scale, but they illustrate the point that this is 2 years of a spectrogram of what the sort of wiggles of the stream discharge look like, and here's also what the spectra of the strain wiggles look like, and then also what the spectra of the tilt meter wiggles look like. And so the thing that we're interested in is this red line that goes across here, and this red line that goes across here, and that over the course of 2 years, that this 78-minute signal is there more often than it's not, and it's incredibly consistent. And there's obviously a lot more activity, particularly in the stream with the summer thaw and the lake levels rising and such, and storm activities. But yeah, it's an incredibly consistent signal. The other interesting thing is that we see this signal strongest at stations closest to the lake, but it's also present at stations that are further away. So just for example, I'm just showing you a record here of, this is sort of an event that occurred, this is June 23rd of this year, so this was a couple of weeks ago, and there's that teleseismic arrival that you should ignore. And yeah, so you're seeing the same wiggles start to show up at the same time on multiple stations, and so this is an interesting signal because we didn't really know about this before, and we're trying to figure out what's going on. And so there are sort of two prongs of that. One is figuring out. One is figuring out what the lake is doing, but another is figuring out whether or not, figuring out if our sort of conceptualization is consistent, that this is the solid Earth responding in a predictable way to a lake load force, whether or not we understand what exactly the lake is doing. So we've been doing some forward numerical modeling to figure out if these different observations at different locations on instruments that are oriented differently and measuring different things, if those observations are consistent. And so, for example, at the top you can see sort of a sketch of what the displacement field would look like, and and then you can sort of take gradients of that displacement field in various ways and compute what the strain field ought to look like. And I don't show you these particular images to show you any to draw any particular conclusions, but to show that particularly that between stations here and these guys up here, there are different predictions for the relative amplitudes of response that you should see if the solid Earth is behaving in a way that we expect it to. So far, all of our modeling observations are consistent with this being a solid earth deformation in response to a lake level change, but we need to do some more checking on this. These are, there's more information coming in all the time because this is a real-time problem. And the big mystery is there's still no clear indication of what is causing the lake disturbances in the first place. For example, there's no consistent meteorological forcer. It doesn't, correlate particularly well with either high wind events or, any of the sort of usual suspects for that kind of thing. So it's an interesting problem, and ask me more about it.
Our next talk will be by Andrea Linos from the Earthquake Science Center, also here at Menlo Park.
All right, so I'm here at the Earthquake Science Center, and I'm working primarily with Andy Michael and Jean Hardebeck here. And what my research is mostly focused on is looking at earthquake rate changes in catalogs. So what exactly do I mean by earthquake rate changes? We have a catalog of data containing the earthquake magnitudes, times, and locations in a region. And a lot of the earthquake changes that you observe, rate changes you observe in that catalog are going to be due to primarily main shock aftershock sequences like the one shown here, this magnitude time plot of the San Simeon earthquake and its aftershock sequence. But you also have another kind of earthquake rate change, and these are earthquake swarms. And these are primarily what I'm going to be interested in, what my research is going to focus on. Earthquake swarms, I'm sorry, is this really, I feel like this is really, okay. In this magnitude time plot I'm showing here, this is an earthquake swarm that occurred in the Salton Trough in Southern California. And you can see that they tend to have very different magnitude time histories than your standard aftershock sequence. And this suggests that they are being triggered by other physical processes that are going on in regions. So they often occur in volcanic regions, but they can also occur in non-volcanic regions, and they can be triggered by things like dike intrusions, fluid flow, aseismic creep, basically any kind of transient process that is altering the stress state in a region. So the current statistical models that are being used to generate earthquake forecasts really don't take into account the short time scale transient earthquake rate changes that these swarms are, and so they appear anomalous. Well, they aren't really well modeled by current forecasting schemes. And so what I'm really interested in is to try and detect these swarms in catalogs and relate them to physical triggering mechanisms, and then see what impact, if any, these transients have on standard forecasting models. So one of the models, one of the statistical models that are currently being used to look at, to analyze and predict the temporal variations in seismicity rate in catalogs is the epidemic type aftershock sequence model. And basically, this just uses a set of optimizable parameters to fit a catalog and explains the seismicity rate in the catalog as the summation of a background rate plus the aftershock sequences of every event that occurs in the catalog. As it turns out, earthquake swarms appear as anomalously high seismicity rates relative to this ETOS model. In this figure I'm showing here at the bottom, this is a plot of an earthquake catalog from Mammoth Mountain in the Long Valley caldera in California. This is showing cumulative number of events versus time from 1980 to 2011. And the blue line here shows the observed data, and the red line shows the fit to the data using this ETOS model. And you can see here in 1989, you have the significant increase in seismicity that's observed in the data that really isn't captured by this model, and this is due to an earthquake swarm that lasted about 11 months that started in 1989 underneath Mammoth Mountain. So the first part of my research is going to be focused on using the ETOS model to try and identify swarms in catalogs, and the study area that I'm going to be focusing on at the start is Long Valley Caldera. And this is an interesting region to look at swarms because a lot of swarms and other earthquake rate changes have been already identified. Besides the 1989 swarm I'm showing here, there have also been swarms in the south moat of the caldera that have been triggered by fluid intrusions. In the Sierra Nevada block just south of the caldera, there have been main shock aftershock sequences following magnitude 5 and 6 earthquakes. And then there have also been observations of earthquake rate changes that have been related to dynamic triggering following the Landers and Denali earthquakes. And so the first part of what I'm trying to do is to use the ATOS model to try and pick apart the spatial temporal evolution of these different earthquake rate changes, and also to see if there's a way that we can distinguish between all these different triggering mechanisms strictly from the catalog data. And then the second part of my research is, given that these earthquake swarms occur, what impact do these changes have on short-term earthquake forecasts? So the current, as I mentioned in the beginning, the current statistical models that are being used to produce forecasts such as the USGS's 24-hour aftershock forecast shown here often assume that the background rate in a region, the background seismicity rate, is constant. But during these swarms, the background seismicity rate increases from 1 to 2 orders of magnitude, which I'm just showing here. So again, this plot up here shows the swarm, the catalog I was showing earlier. This has a background rate of 0.004. If I try to fit the ETOS model to just the swarm itself in 1989, this requires a change in the background rate up to 0.28. So this is a change of almost 2 orders of magnitude. So the main question I want to try and answer is, do earthquake swarms, which have significant increases in background seismicity rate, but often operate on timescales of days to weeks to months, maybe to a little over a year, do they have any effect or a significant effect on these short-term earthquake forecasting schemes? And if it turns out that they do, what I then am hoping to work on is how can we incorporate sort of swarm detection into the forecasting algorithms that are in use today. So that's about it. Thanks.
Continuing in the vein of seismic work, our next speaker will be Danielle Sumi from the Earthquake Science Center. She's actually a National Science Foundation Fellow with us today. Okay.
Hi, well, thank you all for having, a National Science Foundation postdoctoral fellow join your USGS club. I have to first mention my collaborators. First, I'm working under Elizabeth Cochran, she herself is actually a new research scientist at the USGS in Pasadena. She started her work June 6th there. And also, I must mention our international collaborators, Rebecca Harrington and Tobias Horstman, who are at the Karlsruhe Institute of Technology in Germany. So even you biologists out there can recognize an earthquake on a seismogram. And as you can see, it's a impulsive release of energy, easily identifiable, occurs over, has a rupture duration of a few seconds to about a minute. And then if you can see on the seismogram below, is a tremor signal, which looks incredibly different than an earthquake. It has a long duration, and it's also low frequency. And it was first discovered along the Nankai subduction zone in southwest Japan by Obara in 2002. And since this discovery, tremor has been observed in several other subduction zones, including Costa Rica, the Alaska Aleutians, and also most notably in the Pacific Northwest in the Cascadia subduction zone. And also along our neighborhood strike slope San Andreas Fault. If you can see from here, earthquakes, if we're looking along the subducting plate interface, earthquakes occur in the shallow portion of the fault in this locked zone region. And tremor occurs deeper along the plate boundary than regular earthquake activity between what is the earthquake generating zone and this aseismic or stably sliding zone. So tremor is thought to illuminate this transition between the well-coupled high-friction environment of earthquakes and also the stable sliding regime. And further, what's really interesting and kind of the objective of my proposal is that we don't really understand very well how these down-dip region and subduction zones, or further in strike-slip environments, how the adjacent portions of the fault, what they do to influence the upper portion earthquake generating, especially in Cascadia, massive earthquake generating zones. To kind of shed some more light on that possibility is the fact that if we're looking at Vancouver Island, this is the Cascadia subduction zone, and this is the tremor that's been observed there from 1997 to 2007. And as you can see, it looks spatially anti-correlated with the two large earthquakes in the past 100 years, the 1918 magnitude 6.9 earthquake and the 1946 magnitude 7.3 earthquake. Further, if we look at just the local earthquake activity along the Juan de Fuca and North America plates, you can see that even the micro-earthquake activity is spatially anti-correlated with tremor. And so if we kind of steer away from subduction zone environments and look particularly at the San Andreas Fault, with these 30 square kilometer regions, one particularly around Chelem, which is the area that I'm interested in, over 1,200 earthquakes have been identified, and this is from a study by Nadeau and Gilham in 2009 that observed all these tremor events. Also, what's interesting to see is this Chelem segment is right at the tail end of the 1857 rupture zone of the Fort Tejon earthquake that ruptured in a 7.8 earthquake. Also, this tremor is occurring in the 63-kilometer-long section of the Parkfield-Chelem segment of the San Andreas Fault that is thought to be capable of rupturing in a magnitude approximately 7 earthquake. So understanding how tremor and earthquake activity is very important. Also, if we look just in a cross-section depth with distance along strike of the San Andreas Fault, you can see this is all of the earthquake activity, and here's the tremor activity in this region. And all of these colored dots are representing tremor that has been triggered by teleseismic earthquakes. And it seems like the amplitude of stress necessary to trigger these earthquakes was on the order of 2 to 3 kilopascals, which is incredibly small to be able to trigger tremor at the site. So what I'm trying to do, and I just started my position August 1st, is to investigate the spatial and temporal distribution of tremor and these local micro-earthquake activity along the Parkfield-Chelem segment of the San Andreas Fault. And what I hope to do is better understand the range of fault properties that drive failure at this site, and basically how does these two segments of the fault communicate with one another. Also, I'd like to investigate how much deformation is accommodated via that shallow earthquake generating portion of the fault versus the deeper portions of the fault. And then what I'd also like to do is explore the relationship between earthquakes and tremor and the amplitude of stress necessary to trigger earthquakes at the site. And also, if a relationship is identified, how does tremor location vary in time, how does earthquake location vary in time, and how does that relationship change through time? So what I have the great fortune of coming into is since these regional arrays, here is the high-resolution seismic network, and since the Southern California seismic network are located far away, and I would like to incorporate the NCSN network as well, so if you have any information about that for me, that would be great. And what we've done is we deployed the Parkfield experiment to record microseismicity and tremor, where you have to give it some fun acronym like PERMIT. And this was just pulled out at the end of July. And so we have 13 months of data that we're now able to work with that were densely spaced around the Chelem segment. The PERMIT array is composed of 13 stations recording at 200 samples per second. And while there were 4 individual stations, since tremor is this low-frequency signal, we also stacked 3 stations. So we have 3 subarrays that have stations that are spaced on the order of approximately 150 meters apart. And in the first 3 weeks of our deployment in May, we were able to isolate 112 tremor episodes, and which are shown here. You can see these nice, tremor occurring across the array. And what I hopefully will be able to do is locate these tremor and maybe apply what Andrea was just talking about and looking at the relationship between tremor and earthquake activity. Thank you.
So rounding out our paleoseismic session, we have Catherine Scherer. And she is a new research scientist hired at the Earthquake Science Center in Pasadena.
Afternoon, everybody. Let's see here. Could I get everybody who doesn't work on earthquakes to raise their hands? Okay. After that big athletic endeavor you just had, now you feel invigorated, right? But it gives me a sense of gauging who I'm talking to. So unlike the previous talks, I deal with big earthquakes that leave a mark on the ground surface. That's the overall goal of paleoseismology, is to understand the behavior of these large earthquakes. And for the most part, my task is to understand the behavior of the San Andreas Fault, the southernmost San Andreas, and also I'll be starting to move off of that onto the San Jacinto Fault. Look forward to doing that. So some of the questions, the big overarching questions that we ask in paleoseismology are about these very large earthquakes. In some ways, these are very simple questions, but they're also, as we know, very important. How big can these earthquakes actually be? Can you rupture all the way from Parkfield up here all the way down to the Salton Sea, for example? Do they branch? Can you get something that goes from San Andreas onto the San Jacinto? If they do this, how often does that occur? Is that a common problem? Are stepovers and geometric complexity important in these big ruptures? How frequent are different varieties of these types of earthquakes? And then finally, bigger questions: what can rupture patterns, once we accumulate rupture patterns by doing paleoseismology, what can these tell us about relaxation of stress? Oh, is this on a timer? Stress at a point and loading at other points. So I'm excited about these questions in part because they address questions of fault complexity, which are being addressed by other types of research, including traditional seismology, but also pretty robust, and maybe not robust is the right word, interesting models of dynamic earthquake rupture. So just to give you an example of the types of data sets that are out there, this is a combination of maybe sort of 1/20th my work and a lot of other people's work, are rupture histories. So each of the bars that are oriented vertically represent the estimates for age of an individual large earthquake on the San Andreas system at one of the sites with the stars on them. And what we try to do is, given uncertainties in radiocarbon dating, try to string together rupture histories. We have lots of areas for which we don't have sufficient data to go back farther in time, and that's something that I've worked a lot on improving. And so what we try to do is build rupture models that will respect all of the data to the best possible extent. And then questions like, does the north part, this is on a timer, does the north half of this tend to rupture in large earthquakes, and the southern half is in other large earthquakes, and then some overlap in between, or are there other patterns like that? Bottom line is we need additional data in order to answer that question more robustly. So I'm just going to end with a picture of what I was doing yesterday, which this photograph here was taken yesterday. This is work with colleagues at the University of Oregon and also some students that just started helping me out at the site as interns from Pasadena City College. And so I dig large trenches in the ground in order to reveal this type of evidence. This is traditional paleoseismic site trench, and then also some of the larger V-cuts that we do so that we can really see the deformation of these Holocene sediments. And this is an example of what I think the 1857 rupture looks like compared to what Danielle's example. So a couple hundred kilometers away from Park Field. This is at the Fraser Mountain Paleoseismic Site, and so this would be an example of the last time the southernmost San Andreas ruptured. So I'd like to end with a little bit of an advertisement in that I'm a new scientist. I'm down in Pasadena. And so if you're interested in exploring radiocarbon dating, that's something I do a lot of. And also statistics of rare events is much more my game than having the gobs of data that Danielle gets to play with. So send me an email. Thanks.
All right, so we're going to go ahead and change gears yet again to our final topics of the day. Marine paleoclimatology talks. We're going to start off with Nancy Prouty from the Pacific Coastal and Marine Science Center in Santa Cruz.
Thanks, Jason. Good afternoon. In contrast to the notion that life didn't exist in the ocean below 600 meters, we now know that there's a huge amount of life in the deep sea. Deep sea corals, their habitats in particular, are really now known as biodiversity hotspots. And you can see from this diagram, the different colors represent different deep sea coral communities in the United States. And their distribution and their density really correlate with the occurrence of the United States exclusive economic zone. And the outer continental shelf and the EEZ are within the national domain. And so the United States Geological Survey conducts research within this area. And particularly, the USGS plays a role in the ecological assessment of lands that are to be leased for oil and gas exploration, which is managed and regulated by BOMER, but the USGS is tasked with meeting several of the science needs of BOMER. So some of the science needs that we're trying to address within the USGS include providing fundamental ecological information that is lacking in these regions. So this includes areas that are to be leased for gas and oil on the slope, on the shelf, in the canyons, on ridges, seamounts, to provide the science to enable sound evaluation of potential impacts and appropriate mitigations. And this all really is driven home by the Deepwater Horizon spill. And to improve the effectiveness and efficiency of BOMER in managing the gas and oil operations. And really, you know, from my perspective, is protecting these deep coral and canyon habitats where significant activity is or being planned. The deep sea corals provide habitat for a variety of different species, particularly commercially important fish. And so we have a lot of questions about their how renewable are these areas if they're disturbed? What is the connectivity of the different communities? You know, what are their stressors? Anything from trawling to increased sedimentation, climate change, as well as climate change associated with changes in ocean acidification, because there are scleractinian corals that build their reef structure out of calcium carbonate. So to meet these science needs set out by BOMER, the USGS has been involved in developing a program called Discovery, and it stands for Diversity, Systematics, Connectivity of Vulnerable Reef Ecosystems. The bulk of this work is really focused in the Gulf of Mexico and the southeastern United States. We have about 14 sites in the Gulf of Mexico and southeastern United States, and it's a multi-agency and multidisciplinary project that involves geologists, biologists, physical oceanographers, even archaeologists looking at how do shipwrecks serve as substrate for the deep sea coral communities. And we also have a site that's just started in the Mid-Atlantic region that is being considered for lease sale. BOMER estimates about 130 million barrels of oil might be recovered from the canyon sites offshore of Virginia. Our work really came in the limelight, unfortunately, because of the Deepwater Horizon spill. We had coral sites that were adjacent or very close to the Deepwater Horizon spill, and you can see that over here. This is this arrow pointing to our coral sites, and then this is the surface oil slick, the projected oil slick. In particular, we received a lot of attention for our work where we age dated some of the corals in a study that was published in Marine Ecology Progress Series this year, where we dated corals in the vicinity of the Horizon spill, dating back to over 2,000 years old using radiocarbon methods. And this really is important because one of the questions is if these areas are disturbed, whether it's human disturbance or natural disturbance, how renewable are these? And clearly those ages don't suggest renewable in a human context. And I also just want to point out that the work we're doing in terms of being multidisciplinary really is in line with the recommendations that were published in the President's the report, where one of the recommendations was to conduct a joint research program to systematically collect critical scientific data in an area that's being considered for oil, gas leasing, and to provide ecosystem-based science review. So for me, this has been an exciting project because I get to work with a variety of people. The focus of the USGS scientists on this project is are the following projects. We have folks from Gainesville and St. Pete doing fishes and macrofauna trophodynamics and habitat characterization. In St. Pete, we have Christina Kellogg doing benthic ecology, trophodynamics, and ecosystem connectivity studies, as well as Amanda Demopoulos, involved in genetic studies of deep sea corals and associated communities. And then I'm personally involved in the paleoecology of deep sea corals, including growth rates and lifespans, which are relevant to coral archive records. And we have a poster up there that was recently presented at the Goldschmidt conference that deals with a lot of those specific results. So as someone involved and interested in paleo work, the deep sea corals really kind of are a treasure trove of information. They're continuous, globally distributed, they're long-lived, and due to emerging technologies, we can make high-resolution measurements. So we can date the corals. This is a black coral, looks kind of like a bush or a tree. This is a cross-section base, and it really grows like a tree with tree ring structures. So we can both count the bands, as shown here, and then also date it via radiocarbon. And then we make measurements using laser ablation ICP-MS for various elements. Shown here are concentration maps of rhenium, and superimposed on this is the nitrogen isotope record from really the last 1,500 to 2,000 years. And what we're working on now with our results is showing that there seems to be an increase in the nitrogen isotope values, which most likely is coming from nutrient loading in the Gulf of Mexico, and this seems to co-vary with the amount of rhenium loading. And rhenium has a natural source, but there's also an anthropogenic source that is associated with combustion or coal production. So we're working on that. And again, if you'd like to see more details of both the methods and the results, please come see the poster.
All right. So, turns out I'm the last speaker. So, I'm actually over in the Volcano Science Center. I work with John Barron and Leslie Anderson in Denver and Bruce Finney in Idaho State University. And my work is on building paleoclimate records at annual resolutions since the mid-Holocene in Alaska. As some of you know, the North Pacific Ocean varies in a number of parameters at multi-annual and multi-decadal timescales. Most of you are familiar with El Nino. Well, the other dominant mode of variability is also known as the Pacific Decadal Oscillation, a phenomenon that operates on 40 to 70-year timescales. And most U.S. West Coast instrument observatories have only been in operation since the early 1900s, which means something that oscillates at 40 to 70 year time spans is likely to not have a very good instrumental record. And so to fully understand the range of variability possible in the North Pacific, you have to turn to paleoclimate methods. And so I've been working in the Gulf of Alaska, which has a very strong relationship to this PDO phenomenon. It also has a unique sedimentary depositional environment that is really very, very useful for studying high-resolution paleoclimatology. And these are the anoxic fjords in southeast Alaska. They're anoxic because there's a very shallow sill in between the fjord itself and the greater ocean beyond that sill. And the sill helps to contribute to the maintenance of a very anoxic water mass in the bottom of the fjord, so that any organic signal that's exported from the water column to the sediment is preserved in a very, very clean way. It also minimizes the amount of bioturbation of these sorts of paleoclimate signals. So working with a pair of 18-meter-long sediment cores collected back in 2004, I've been doing core face XRF geochemical scanning and computerized tomography to be able to pull out very, very fine-scale paleoclimate signals. This is an example of the kind of data set that can be generated by one of these XRF geochemical scanners. It's a 7-centimeter thick section here, and every data point is done at 200-micron step size, which for most paleoclimate work is an incredibly high spatial resolution. The other side of what I'm trying to do is, obviously, if I want a very robust paleoclimate signal, I have to understand what the modern calibration really looks like. And so I've been pairing these paleoclimate signals with short surface cores to understand the modern sedimentary environment. And what we find in our computerized tomography scans, which is sort of related to sort of a three-dimensional X-radiograph, an X-ray of a sediment core, if you will, the background sedimentation is controlled primarily by laminated intervals. However, superimposed over that background lamination accumulation, there are also a series of other kinds of events, such as turbidites, flood deposits, and even occasional bottom water oxygenation events. So despite these little complexities, which using these high-resolution techniques we can identify, it turns out we can still pull out actually a regionally important climate signal from these sediments. So what I'm showing you here is actually the instrumental PDO index from the North Pacific compared against a modeled summer productivity anomaly near the region that I'm working in. And what I'm comparing against is actually the XRF intensities for bromine. It turns out bromine has a very strong affinity for marine organic matter. And in fact, that affinity is actually confirmed with these organic matter isotope results, which indicate this part of the record is very marine dominated. So we can see that the oscillations in this bromine intensity tend to follow pretty closely with the PDO index, which is very encouraging. So what's next for this study? Well, it turns out I've only been working on this project for about 8-10 months or something like that, which means I'm only about 50% of the way down these big, massive sediment cores. However, the results that we've been getting so far, though very preliminary, are also very exciting. So this is that same figure I just showed a few moments ago. In this case, I want to show the sulfur and the iron relationship across a turbidite in these cores. And what we find is that iron, in some portions, tends to follow very closely with sulfur, which suggests some sort of iron sulfide precipitation or accumulation. However, even within the space of only not even a half a centimeter, that correlation falls off very quickly, suggesting that we have actually a change in phase in the iron record. And so that geochemical complexity suggests we need to do more work, of course. So I'm going to be combining these XRF scanning results with detailed thin section microscopy. And we'll be using SEM methods, diatom microfossil assemblage information, as well as synchrotron geochemical analysis. And so ultimately, the hope here is to be able to develop a high-latitude North Pacific paleoclimate record with annual resolution. So that's all I had to say. It also brings in... Oh, of course. Well, it turns out we're not quite done with our presentations. What I was going to ask was a kind round of applause for all of our people, but let's hold off so that you can say a word. That is correct. Sorry about that. Here you go.
Well, the first question is, did I really want to, or did Rama twist my arm? But I want to, my name is Jeff Kay. I'm the acting regional executive for the Pacific Southwest area. And you've really, this has been a wonderful afternoon because it reminds me, I was a scientist once. I really appreciate the opportunity to be here, to hear about the great work that you're doing, to see the minds that we have here, all working to solve some important societal issues that are critical to our nation. The bad part about giving somebody like me a microphone is that I don't get to deal with science anymore. I end up dealing with budgets and out-year budgets and how do we keep everybody employed and how do we work with our partners and this and that. And what I want to do is right now is encourage you. You hear what's going on with Congress and the White House and how they're disputing about budgets and we're downsizing and all of this stuff is going to happen. But societal issues are not going to go away. And there's all this grappling about a few percentage points of our budget that Congress will try to take away, but that's going to leave 80, 90, 95% of our budget to do really good science. And I remember early in my career, I'm a wildlife biologist by training. I studied at the University of Idaho, and Morris Hornacher did some pivotal mountain lion research in Idaho, and I was having dinner with him one time. He was about ready to retire. I was working on my master's degree and worried about a career. And of course, this comes across chauvinist. You just have to know Morris. But we're talking about careers, and he looked at me and he says, "There's always a place for a good man." And I think there's a message there, is that in spite of all the crap we hear about budgets and all, we will continue to hire scientists forever in the U.S. Geological Survey. There's always going to be a place for good people. You got some very good advice here today. As a manager, when we look for scientists to hire, you as postdocs are, this is kind of your chance to prove yourself. Learn the business of the business. Your PhD teaches you how to do science, but there's a business that goes along with it. It's how do you look at this big amorphous societal issue and grab something out of it that you can conduct a research project on. Clean, clear objectives and conclusions and results that can come out of that. How do you do that? That's another an art part of the science that you need to learn. And how do you, no matter where you are and who you work for, you're going to have to find money. You're going to have to convince somebody else to give you money, whether it's somebody within the U.S. Geological Survey or somebody outside of the U.S. Geological Survey. So how do you cast that? How do you pitch it? How do you bring in money? So here's your chance to kind of prove yourselves on those fronts. Publish in peer-reviewed journals. Learn the business of the business. How do you secure funding? How do you work with partners? The networking thing is huge. And don't be afraid to call people and talk to people. And I'm going to be around for a little bit and happy to chat with anybody that has any questions. But I just wanted to thank you so much for what you're doing. You're doing great work, and just keep it up. And the round of applause right now would be very appropriate. Right? Thank you all.
Okay, so that brings us to our poster session. As you can see, we have posters here. We have posters out in the hall. Refreshments in the back. Again, I'd like to really thank all of our presenters today for making the trek here and distilling their science down into 3 to 5 minute snippets. I know that's not easy. So thank you again, everybody. I know, the last time I did this, it was a whole presentation of questions. Yeah, I know. But now,